Hello everyone, this is Physics 103. This lesson is on molecules and solids, and for this lesson we are going to talk about molecular spectra. So, molecular spectra, just like atomic spectra, is the energy given off in discrete amounts of molecules. So, if you would recall that atomic spectra, when you pass through a light of all wavelengths in atoms, the atom will only emit certain levels of energy to the screen. So the same thing happens with molecular spectra. If you try to pass in light of all wavelengths to molecules now instead of atoms, these molecules will actually give off discrete energies rather than giving off a continuous spectra of energy. So for our study in molecular spectra, we will first consider the rotational energy associated with molecules, the vibrational energy associated with molecules, and then we will try to combine these two and see how the energy is quantized. So let's first start with rotational energy. So consider this system of a diatomic molecule. So you have here M1 separated by M2, and they are rotating at a fixed axis. So for example, our fixed axis is here. It's not necessarily in this area, but for the sake of simplicity, let's fix this axis in here. So they are rotating in this axis, and we want to find its rotational energy associated to it. So we know that the any object that is rotating will have an angular momentum associated to it. So we know that angular momentum is equal to I omega, where I is the moment of inertia of this system about the axis. So its kinetic energy, meanwhile, is given by K equals 1/2 I omega squared. So if we combine these two equations, we will get K equals, or the kinetic energy would be equal to L squared over 2I. Now take this example wherein there is no potential energy associated to this kind of system. So we are to say that this system is purely kinetic. So its total energy is only given by E equals L squared over 2I. Now, let's try to look at this angular momentum. So when we solve the hydrogen atom using the Schrödinger equation, we noticed some peculiar features of its angular momentum. So for a hydrogen atom, its angular momentum is actually quantized by the angular momentum quantum number L, h bar, where L equals 0, 1, 2, and so on. So this is for the hydrogen atom. So surprisingly enough, this, if you want to call it formula, is actually also obtained if you try to solve the Schrödinger equation for a rotating or for a rigid body rotation. So we will not attempt to solve the Schrodinger equation for a rigid body rotation, but it is left that to say that this is the same quantized angular momentum for the rotating two atom system, or the rotating molecule. So what happens to our total energy if our angular momentum is quantized? So E now becomes L, or square root of L plus 1 squared, sorry, there's an H bar, over 2I. So this becomes E equals over 2I. Now, if you would look at this formula, you would see that the rotational energy associated to our system is quantized by L equals 0, 1, 2, and so on. So these are the rotational energy levels corresponding to the angular momentum quantum numbers. So at L equals 0, let's try to see what happens. So at L equals 0, E is 0. At L equals 1, so we have 1 plus 1 h bar squared over 2I. So E equals, what's this? 2 h bar squared over 2I, or just simply E equals h bar squared over I. So if we try to plot different values for E with respect to L, we would notice that it is actually quantized. So at L equals 0, we have a value of E to be 0. At L equals 1, we have a value for the rotational energy to be h bar squared over I. At L equals 2, we have our value to be 3h bar squared over I. So what can you notice? This energy is in quantized by L. So this is very interesting because the quantum effects from solving the angular momentum is reflected also in molecules. So previously we only observed quantum effects in atoms, but now we are seeing quantized effects also in molecules. So in the next video, we will see how vibration in molecules is also quantized.